It is indeed a pleasure for me to introduce the speaker to this August gathering. As you all know, microplastic pollution, it is a very serious, I should say, it is developing environmental problem in aquatic fields. In fact, it's a serious threat to marine systems and human health. Global production and consumption of plastics have continued to rise, and the problem is that most of us use and then toss way more plastic than we need. Anyway, so we are going to listen more from the very distinguished speaker, and it is my proud privilege and honor to introduce such a distinguished academician, Professor Balasubramanian. So just a minute, let me introduce him. So Professor Balasubramanian is a Dean Academics and Professor at Department of Metallurgical and Materials. Why it is coming again and again? I don't understand. Let me see. Yeah, so Materials Engineering BIET, Ministry of Defense, Government of India. He has published more than 280 research review articles in international peer-reviewed journals and has received more than 5,200 citations for his research work. Professor Subramanian is highly acclaimed for his contribution towards polymer processing and fabrication for various applications, which include development of antibacterial textiles, smart textiles, hydrophobic coatings, ablative materials, fire retardant fabrics, wastewater treatments, and polymeric nanocomposites for defense applications. Professor Balasubramanian was actively involved in the development of various research laboratories like Polymer Processing Lab, Nanotexturing Laboratory, Advanced Characterization Laboratories, which include field emissions, scanning electron microscope, high resolution, transmission electron microscope, small angle X-ray scattering lamp, so on and so forth, additive manufacturing laboratory, etc. The research activity of Professor Balasubramanian research group can be classified primarily into 5 categories: wastewater treatment, smart textiles, biomimicking of the nature in polymers, structural composites, advanced coatings for defense applications. Professor Balasubramanian has been recognized by Royal Society of Chemistry for being one of the most cited author of the year 2015 for his erudite work on superhydrophobicity. He has been recently awarded with the prestigious award of Technology Innovations in Petrochemicals and Downstream Plastic Processing Industry from Ministry of Chemicals and Fertilizers, Government of India, for his contribution in wastewater management and design of advanced coatings. In last 5 years, he has developed various technologies and secured them in the form of patents and published in international peer-reviewed journals and international conferences. So with such an illustrious career, we are really very delighted to have Professor Balasubramanian with us. So with this brief introduction, I now request Professor Balasubramanian to take over. Thank you.
Thank you very much, Chairman. Am I audible?
Yes, sir.
Yeah. Okay, thank you. With the permission, can I start, Chair?
Yes, sir. The screen is already shared. You can speak, sir.
Okay, fine. So thank you very much for such a very elaborate introduction. Maybe so now the expectations of the audience to be mapped and matched. It's not that simple and easy, especially in the online mode, but I will try my best. So today, sorry, first of all, sorry that I shifted my timing from 10:30 to 3. My sincere apologies because of some personal commitments. Anyhow, so the title, as you see in the national webinar, is on microplastic pollution, role of educators and researchers. If you look into the contents where I'm going through, is like, what is the global view? The concentration of microplastics in India, and what are these microplastics made up of the constituents, various additives in microplastics where you have some toxic metals. Those things should be covered. And then some aquatic pollutions, what type of pollutions we have, and the health hazards. And I'm going to give about 2-3 case studies of how our group had contributed in utilization of the waste plastic. If you look into the global view of microplastics, see, if you see there less than 5 millimeter, if you look into the concentration, there are various sediments spread across the globe. Maybe the various colors which are shown here are not the colors of the fishes or the islands. It's a concentration of microplastics which are having dimension less than 5 millimeter, settling and sedimenting and floating across the aquatic areas. So, it's very, very, very dangerous number. Actually, if you look into it, it's spread across north, south, east, west. You can see Arctic, Antarctic, it has crossed everywhere. So it is definitely not a good sign, definitely because it's a non-biodegradable, and it's giving lots and lots of pollutions, especially to the aquatic. So food chains are having severe issues. So these are all the, the concentrations where it is shown across the globe. If you look into what you see in India, as per the Central Pollution Control Board data, 62 metric tons of solid waste was generated in 2015, 62 metric tons. And the second number, if you see, only 82% of such waste are collected. See, the balance 18%, we don't know where they are. They are there somewhere in the form of litter. And out of this, only 28% of the wastes are treated. Means, 72% are just dumped. It's just spread across everywhere. And this is the data which is in India. If you see, we are given the details of the place, the size of those particles and the plastic materials. How are they present? Either in the form of a film or a foam or whatever, fibers or fabrics. But if you see, most of the polymer types are commodity plastics. Let me explain what is the meaning of that. Normally, if you look into the polymer plastic technology, you can classify into 3 major categories. One is the commodity utilization, commodity market. The second market is the engineering market. And the third market is the specialty market. Commodity markets, if you see, right from your carry bag, milk pouches, to refrigerators. Engineering plastics, which are going for high-end engineering applications like nylon, polyesters. These go for engineering applications. They go for ropes. They go as gears. They go for glass reinforced systems. And they go for good level of engineering applications. Specialty applications is a new category where polymers like polyether sulfones, polyether ketones, very specific applications. Like 316 metal, a medical implant was replaced by titanium alloy. But now people are thinking of replacing even that with a material called polyether ether ketone without compromising weight to strength ratio. So we are talking only about the commodity plastic. If you look into the places, it has covered most of the rivers, the best rivers, and most of the coastal areas. They are completely spread out with 72% of dumped waste plastics, either in the form of polyethylene, polypropylene, polyvinyl chloride, and some polymers like polystyrene. These are all thermoplastic materials, means they can be recycled, but still we are not taking it seriously to recycle it. So this is to be addressed, and this microplastic contamination doesn't get degraded also. See, the degradation is not at all possible with such kind of high molecular weight polymeric materials. So it's not a good sign, but this is a real fact and the real sign. Now, as I said, all these are thermoplastic materials, but these thermoplastic materials, next slide, please. These thermoplastic material have various kind of additives when it comes out of the polymer reactor as a gluey, gloopy type of high molecular weight material. We need to process. They use various processing aids. Like it's like, again, I always give in my lecture the simplest example, wheat flour. Wheat flour is just a flour, is a powder, fluffy. To make it into a dough of wheat, we'll have to process it with some additives. So the additives are oils, water, salt, some flavors. So in the similar way, polymer, once it comes out of the reactor, should be processed and compounded with additives. And these additives are fillers, reinforcing agents, stabilizers, UV agents, heat stabilizers, lubricants. So these are all some of the various additives which are to be mixed and compounded to come out and process in the processable form. So for that various additives, and these additives are compounds of either calcium, magnesium, sometimes chromium, sometimes silicate, and also something like the stabilizers. If you see, the anti-corrosive coatings always use tin and cadmium based systems. Okay, and these are all really toxic. So these, and colorants, we use various colorants and dyes. So these colorants and dyes, for example, blue color is from a material called phthalocyanine blue, where this material has got copper in it. Phthalocyanine green, the green, beautiful green color which comes to all the car finishes, the green paints of car, they are all having phthalocyanine green, where they have nickel at the center. And there are some chrome colors which give some orange tangy color. So these colorants and other things are also present in the plastics, which are causing various aquatic pollutions as well as land pollutions across the globe. So that composition and that variation is also shown in this particular slide. Next slide. What it really does, if you see, it nicely falls as a member in our life cycle, in our food cycle. See, the man is throwing that, and when he's throwing, it goes into the aquatic. And when it goes into the aquatic, normally if they are finer particles and if they are getting sedimented, these finer particles are also consumed by various microorganisms. And these microorganisms are again picked up by the aquatic fishes. Then again, the fishes are picked up by the birds. Then the birds are then picked up by. So if you look into the food chain, the food cycle, it goes everywhere. It goes everywhere. It is there. It is almost. It is not like oxygen, but it's visible, but we are not able to control it. We are able to see it, but we are not able to control it. We will have to take care of this, because this kind of pathways to the ecosystem is more dangerous. Why? Because recently there was a paper in it was Nature. It was one of the Natures, because Natures are got about 10 to 15 different kind of subdivisions. In one of the Nature's paper, we found that these microplastics could result in mutagenic. See, we know that all these metal oxides are all carcinogenic, means cancer producing. But they have found that some additives and some plastic materials, which are thermoset systems, especially the epoxidized based and cyanide ester based, they are even causing mutagenic effects, means it mutates the genetical activity. So it cannot be taken so easily. So, this is to be addressed. Definitely we'll have to address this. So it has become a part of the food chain and the food cycle. Next slide. You see the aquatic pollution. If you look into this, that's not That's not the bed of water, it's the bed of plastics. And these plastics which are floating, normally plastic materials have the density ranging from 0.8 grams per centimeter cube to 1.7 grams per centimeter cube. So these plastics which are just floating on that water, they are all polyethylene and polypropylene, which are having this density of 0.8 to 0.9 or 0.9892 grams per centimeter cube. You see that it's completely sealed the skin of the bed. Sealed the skin of the river bed means there is no UV penetration through the aquatic system. So when there is no UV penetration through the aquatic system, it becomes dark inside the aquatic system. So the planktons, phytoplanktons, the food chain is really killed. So, and they are non-biodegradable. It's going to lie there. So based on this kind of contaminants, the microplastics which are having less than 5 millimeter, they are primary. And microplastics resulting from weathering and fragmentation are secondary. And these particles then further go into finer and finer, they call it as nano. These are the three major classes within the microplastic systems. And though they are not biodegradable, as I said before, they have some soluble salts as an additives. And these soluble salts result in toxic ion pollutants. So it is definitely a threat for global system. These are some images which we have taken from public. You see that animal stomach and liver, once we take it out, if you see most, I think this is known across everyone, like the fishes close to the Bay of Bengal, they are realizing that it has got some arsenic content and some deposited mercury ions. So I think it was 10-15 years back, this had become a big news, and the toxic metal ions are there in the aquatic species. That's fine. But these last 5 years to 8 years back, they found plastic particles inside these fishes. Really surprising. Inside the fishes and aquatic, this is not a good. And they were able to see even close towards the placenta. The placenta is the one which connects from the mother to the baby before it's getting born. Even there, they were able to see some particles of plastics. And respiratory issues. See, as I said, recently people had been extensively using this N95, N99 synthetic non-woven mask. And these masks, it could be from any company. It could be from Venus, or it could be from Wildcraft or anything. But still, the fibrous particles of these masks, non-woven, can enter through the respiratory duct, and they can sit inside there for years and years. It's definitely causing some trouble there, which will result in asthma and some other respiratory ailments. And this is a very famous, popular news. I think you all would have seen that 52 kilograms of plastic was recovered from stomach of a cow. Because that's it. I think because these single-use plastics, they seem to be very lightweight. They seem to be very nicely chewable, because these herbivorous animals have got fantastic teeth. They can grind nicely, and they like this soft touch of your plastic. And they just, though they knew that it's not edible with their fifth sense, definitely I think they take it because they like to chew it. And with the other food, it gets inside, and it's really a dump, and it's really spoiling that food chain. If you see that the degradation routes, the plastics lying on the aquatics, there are various degradation routes. Solar is one thing, and oxidation. Biofilm means barnacles. Barnacles are some of the species, aquatic species. They initially form biofilm on the plastic. After forming the biofilm matlab, it's very simple. I think you would have got honey. If you see the money plant which is kept inside the home, you take a bottle and you put some water and you put this money plant, and like you invite more Lakshmi's blessing at home. But what happens inside that bottle, after 1 or 2 weeks, you will find a very nice slimy scum on the inside of the bottle. That's called biofilm. And that biofilm keeps on propagating, resulting in the food chain of planktons, phytoplanktons, and barnacles. So these barnacles are really around across these particular plastic materials. And these barnacles, when they try to degrade, though these plastics are not degradable, they try to take something from them, and this gets into the food chain and goes to the next level. So these biofilm is really not good. And with this oxidation and biofilm growth, yellowing of the plastics takes place. And so because of seeing that yellow color, some birds can pick it up, thinking that there are some pulses or there are some morphological changes. It results in degradation. It's not degradation. It's a chain scission. I would call it as chain scission, which is not getting degraded. So these things are still remaining in the atmosphere. So these sources of primary and secondary, they are definitely resulting and causing these kind of degradation routes in the environment, which is not completely getting biodegraded. So now, okay, we had been talking all the bad things last 10-15 minutes. Now let us think what can be done, because we know we cannot avoid. I think I want all the audience to look around, sit and look around across you. And can you avoid this plastic? You cannot. You cannot 100% avoid plastic today. You look around, you'll be sitting on a plastic chair. You sit on the table, you'll be having plastic pen. You'll be having plastic tops. You'll be having curtains. You cannot get rid of it. So now, how do we try to improvise upon in using such kind of plastics? The awareness has gone to the world at least to 40-50% that we should not bin the plastic just like that. At least in Pune Municipal Corporation, we are segregating the synthetic and non-synthetic and organic type of bins. So it is happening. The awareness has come. But now I want to show you that in our group, how we utilized these plastics in the form of a case study, and we developed some good products and good projects where we came out with some patents also and with some awards also. Let me start discussing the first one. Very interesting. Styrene malic anhydride. That's all. It's not a rocket science, simple chemistry, 11th standard chemistry. I just want you to remember SMA means styrene malic anhydride, full stop. Styrene, polystyrene, you know, the scales which are transparent scales that your kids carry to the school, they are all polystyrene. And it is a commodity polymer. And the bean bags are having some styrofoams, the beads, the thermocoals. It's a thermocol, they call it, but they are technically called as polystyrene beads. They are polystyrene. These beads, we picked up these waste styrene beads and we tried to do some functionalization of these polystyrene with some malleated systems. It's a chemistry, it's a synthetic chemistry, simple chemistry. So we malleated this styrene, and these malleation resulted in functionalization of our styrene. And then we were able to make it specific for adsorption of toxic metal ions. So what I'm trying to tell here is, normally membranes are used or zeolites are used or various systems are used for adsorption of toxic metal ions. So in our case, we used waste polystyrene beads. In the waste polystyrene beads, we did some surface functionalization and we worked on the adsorption of some toxic metal ions. And we worked on copper ions, nickel ions, cobalt ions, zinc ions, auric chloride, which is gold 3+ ions. And we found that they are very effective in adsorption of these metal ions. I think minimum was 60%, maximum we were able to get about 85% adsorption. And we were able to adsorb. After adsorption, we can dissolve, adsorb, dissolve, adsorb. So till 5 cycles, we were able to be very good. It didn't stop there. If you look into the image where we got SMA bead, which is like a sabudana, bead, but copper has got blue color, nickel has got green color, cobalt has got a nice purplish pinkish color. So what we did, we were able to take this particular material after adsorption we were able to develop some conducting inks. I repeat, styrene, which is a waste system, we surface treated it, and then we were able to absorb some toxic metal ions. And these metal ions were used with these particular beads for some very, very basic conducting inks or conducting type of things. So what we were trying to say, I'm not completely recycling it. If you look into the circular economy part, which is what is a circular economy, is getting reuse, 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 reuse. So we are trying to reuse it, reuse it, reuse it. So this effort was found to be very good. And we got a good output out of this. And this particular study had helped us in supporting and getting some funding from atomic research. The next one, we didn't stop there. What we did is, we used this styrene. With the styrene, we incorporated some sawdust, and we had incorporated some, incorporated even rice husk also. So what we did, we were able to make some, I won't call it as 100% composite bead, but we were able to make beads of styrene malic anhydride sawdust, which was able to have some adsorption property also. In fact, this one had given very good adsorption for dyes. If you look into the paper, on the paper, it's very easy to write with your colors, the colors, rather than pigments. Your dyes have very good adsorption. So what we thought in this is, we can make a cellulosic system where sawdust has got cellulose, hemicellulose, lignin. So this cellulose will have good adsorption of dyes. So we incorporated this, and we worked on some adsorption of dyes, and we got some very good adsorption. It was able to have a decent adsorption, and this paper was published in even Environmental Science and Technology. It's a good journal. So we were able to get this adsorption. So we tried to use as a composite bead. Then what I would like to say is, from the styrene beads which floats on water, if you see these packaging styrene is so light in weight that it can very easily enter your nasal cavity, because they are so lighter in density. But they are very nasty. They are so static. They are so polarized. They don't, if you rub them, if you rub these polystyrene of this thermocol, you can't get rid of them from your hand actually, because it's got so statics. So it's not easy, but we tried to use that, and we were able to come out with some very interesting product. And we are scaling up now. We have done only the batch process of this. Now we are involved in scaling up this system. Next one. Next slide, please. Yeah. Next one is very interesting. Actually, this thought process had come to my group in 2012. That how do we use these waste plastics and rubbers and all these things? How can we take this particular system? How can I reutilize? So in 2012, we filed a patent. The patent got approved only in 2010. We recently got this patent approved, where we had made extensive research on using any type of plastics. Especially the major classification is thermoplastic, which is recyclable, and thermoset, which is not recyclable. So thermoplastics, we had a shredder, we had a recycler plant with us as a consortium, and they were shredding us, and they were giving us all the plastic materials, thermoplastics. And rubbers, we have our own shredder. We shredded all the rubbers, and the shredder can very easily separate the rubber as well as your other cords. There are various metal cords also in that. We separate that. And then we were making our own compositions. Along with the gravels, we were able to make very good road material. So we were able to develop, make some roads where at least, you can patch up the potholes, at least during the severe rainy season. We started in that mode. So from 2010, we had been evolving in working on that. 2014, we had laid a good road. But the problem of that road in 2014 was that was found to be more expensive than the existing technology of roads. Then in 2018, we revamped again, we reformulated, and we had a very good collaboration with the real-time Pune municipal road laying people, with our institute, and with the support of DRDO has got CC people in Hyderabad, Secunderabad. So with their support and we started to rework on it, because lots and lots of masks materials are now produced now. This synthetic masks are really really a big challenge for the future. So what we decided is, why not we use all these thermoplastic waste, we shred them and make some road material. So we really went into a big bang where the road institute normally gives a certification. For getting the certification, next slide please, for getting the certification, we'll have to really make some prototypes. So these prototypes were made and these prototypes were tested. College of Engineering Pune has got their own road research department. So few samples were sent there also for the testing, where we found that we were exceeding the limits with respect to the properties. In fact, if you look into that Marshall flow and Marshall cohesion, these two things control the road properties. So we were able to really get into the range of their requirement. So we didn't stop there. So with our product, next slide please, we didn't stop there. What we did is, we a municipal corporation, this is post-COVID thing. We discussed with them and we said that Panshet is one of the beautiful spot. If anyone from Pune comes, Panshet is most scenic spot in Pune. We said that, but it's not highly globalized, so it's a very organic place. So where there is no mobility of vehicles, as well as the mobility of humans. So we decided to lay some roads with our formulation, as well as both the middle base layer, middle layer, as well as the top layer. These are the activities which we carried out and we were able to make, and it's successful. And the patent is also granted. And we recently, our group won a very good national award on this technology also. Now, next case study. This is the final case study. As I was saying, recent studies have shown that 3 million masks per minute are used globally because of this COVID pandemic. And continuous and long exposure is definitely affecting the nervous system. So these are the data collected across from good citations. Then it also affects the ecological balance, the flora, fauna, which we had explained before. Not just restricts the water percolation, but it also damages the fertility of the soil. So these are all the huge, it's a challenge. In fact, 2019, Fraunhofer and Max Planck in Germany had initiated of reutilization of synthetic mask for something, but they didn't mention about the final application, but people are really working on, big research institutes are really working on how to reuse such synthetic masks. So with this, we said, like, the synthetic mask, how good is that? So we want to get rid of the synthetic masks. So for that, our institute, we got a filed patent and approved patent where we were able to develop environmentally biodegradable system. Means the mask material is going to be biodegradable. It has got antimicrobial properties. It is cotton-based fabrics, and it's nanofiber with herbal extracts, and it has got the super hydrophobic property also. So we want it's like a competition close to synthetic masks. So that was the thing which we thought of, and it was completely a natural system. We had done the material studio as well as the BioVia, where we want to understand the interaction of the herbal extracts along with your fibers. And these nanofiber materials, I will explain what these fiber materials are. We scaled up very nicely. It has shown good porosity, whereby it was supporting the breathing. Normally for masks, the breathability is a big issue. Synthetic masks, breathability is always an issue. But in our system, we didn't want to compromise. Without compromising the breathability, we were able to develop some system which was showing water repellency. So the mask material on the outside will be showing water repellency, and on the inside, it will be having a water absorption property where the sweat can be absorbed. And the middle layer has got all your herbal stuff where it has got this antimicrobial properties. In fact, In fact, some Siddha doctors and Ayurveda doctors had approached us so that they can use this for their asthmatic patients also. So we were able to come out with this system. This was actually a system where we had developed this fabric material for the submariners who do the maintenance for 7 days without showering. So they wanted antibacterial fabric material, but the existing antibacterial fabric material is a synthetic system where it has got nano titanium dioxide and zinc oxide. But we had made it herbal, where it will be having neem oil and eucalyptus oil and some clove oil in the form of electrospun nanofibers. Then these fabric materials had shown fantastic biodegradation. 45 days, it had got about 75% of weight loss with cow dung, cow urine, and jaggery. So that kind of material, the fabric material we had with us. So then we were claiming that why not we develop that in the form of a mask. So we developed this mask, which was called as Pavitrapati, which is a biodegradable mask. We got the registration done in India for manufacturing. The technology was transferred for free to about 8 companies. And this technology was transferred for free. It was for the national cause. So we didn't make any money out of it. But the company who had taken the technology, in 8 months' time, they had a business of about 8 crores. I repeat, in 8 months' time, they had a business of 8 crores globally as well as nationally. The 2 leading mask manufacturers are Siddheshwar as well as Venus. These 2 companies took the technology and they took out the technology to the next level. Next slide. The nanofiber which we have seen here, these are all the back, please. Back. Oh, aram se. Yeah. So yeah. Back. Yeah. See, if you see this, you are having this super hydrophobicity, and then we are able to see the Bacillus aspergillus, which is the cow dung bacteria, which is enjoying the meal of the polylactic acid and cotton. See, polylactic acid and cotton, they are nanofibers which are spun by electrospinning technology. But ATIRA is the Ahmedabad Textile Research Institution, where they can electrospin 2 meters width of the fabric material very nicely. So we were able to spin all those things and scale up. And the company had taken the technology and then they were able to replicate it. Next slide, please. Where you can see the nanofibers and the biodegradation happening. Next slide, please. Where you are able to see the, like various compositions and how we had used the biodegradation. As I said, 78% degradation in 28 days of time. So we are able to, as you could see, in all the case studies, the first 2 case studies were how do I go as a part of circular economy? And the third case study is how can I replace, making an effort. So we are supposed to make an effort of, we cannot replace overnight. Plastics cannot be replaced overnight. I am a polymer technologist. Let me tell you, you cannot replace plastic overnight, but efforts are to be made in developing biodegradable plastics like polylactic acids, polycaprolactones, polyhydroxybutyrates. These are all some of the few examples. But for engineering applications, we need to think of reinforcing such kind of plastics with some natural fibers, okay, which our group is doing, but that's a different topic. So today I just want to see, show a snapshot of about 3 case studies. So what I want to tell the audience is, see, the synthetic mask was getting replaced by a face mask, which is biodegradable without compromising porosity, breathability. And antiviral property, we were not able to test, but we were able to do a test with an amino acid where it had the property of neutralizing the amino acid. So the virus is having any, kind of amino acids, and these can be neutralizing even amino acids. So all the additives, the herbal extracts which are gone into this mask material of nanofiber, they are all as per the Ministry of, it is, I forgot the ministry. So those constituents are really there. It's not like any different constituents which cannot be used. So these natural herbs are always we know that they have got the best medical properties, But in our case, we replaced it and it had shown a good output. In fact, the mask, next slide, please. In fact, the mask, next slide, please. In fact, the mask, when we signed the MOU, immediately, you know, they said at least we will give 0.1% of whatever we have made. So they wanted to give some royalty, and that again, we took those things with the initial whatever the company had made of 2 crores. Initially, we took it and we gave it back to the society. You know, that was given again as a mask manufacturing for all the kids who are residing in the orphanage, which is next to our institute. So we were able to circulate it, and I think we were successful in. I won't say that we had 100% successfully replaced the synthetic N99 mask, but yes, we were equally competent that we hit a good market. Next slide, please. So what I am also just a researcher. I cannot say that you should do this, you should do that, because research with respect to reutilization of plastic as well as microplastic is an evolving process. It's happening every day. So we must try to reduce, substitute, recycle, and dispose. We should reduce the quality and quantity in the system. How much quantity we use in the system should be replaced. Now, if you go into DMart is not giving you any polyethylene bags. They have started giving some, you know, paper bags. Then substituting plastics with alternative materials and delivery systems. And we should design, when I take a material, I should think of immediately reusing it and recycling it. That's what I should think of. Then the collection capacity, though we have the collection capacity, the segregation capacity is very important. After segregation, how do I reuse them is also very important. How do I rescale it up? Like, for example, polyethylene terephthalate, PET can be repolymerized, means depolymerized, so that the monomers can be taken back. The Reliance Industries have started doing that with all their waste polyester fibers. And reducing the post-collection environmental leakage. Yes, it should not be taken it for granted that we put it and put it in the garbage without knowingly. It cannot be contaminating our soil or as well as the aquatic systems. So these are my groups, and these groups, as I said, is working on as introduced by the chairman. We have various subgroups, and this part of the work is from the green technology group, where this green technology group works on circular economy, reutilization, reuse, biochars, environmental treatment, effluent treatment. So this is the type of things we work on with this subgroup of green technology. Last but not the least, as a famous quote of late Dr. APJ Abdul Kalam, you cannot change your future, but you can change your habits. And surely your habits will change your future. Thank you very much. Jai Hind. Hello?
Yes, sir. Thank you very much, sir. Yes, sir. Yes. Thank you very much, sir. The audience, we learned many new things today. There are many faculty members, teachers, and research scholars, and some students here. You have heard about microplastic pollution. Microplastic are particles which are having some dimensions less than 5 millimeter. So they are much more dangerous than the real plastic waste that we are generating now. And today we heard about a very important thing, that is replacing the normally used N99 mask with a biodegradable mask, which the speaker said his research team, they could develop the technology and transfer the technology also. We are quite impressed with that kind of mask. As you know, we are all using, lots and lots of many number of masks, and tons of plastic is being just thrown away, and kind of plastic management is a very challenging subject, as you know. And working in this kind of subject itself is very, very important. Now researchers and educators who are here, If you have any question that you want to ask, sir, you can ask. I heartily congratulate the audience, and really I'm very thankful to the speaker because he had some medical emergency in his family, but still he could be somewhere and then give us this lecture and make it for all of us. Sir, thank you very much, sir. Participants, do you have any questions? Do you want to interact? You can post it in the chat box. I would take it forward to sir. Anyone has any question?
I'm very happy to see there are 160 participants. So
Yes.
at least I will be very happy to take 1 or 2 questions, ma'am, if time permits.
Yes, yes, sir. Just, yes.
Can I ask?
Yes, sir. Sure, sir.
Quite some years back, in Japan and Germany, there were uses of plastic as a fuel in iron blast furnace. But somehow that idea didn't catch up. Can you tell us why?
Sir, good question, sir. You are Mr. Adamu Balarabe?
Manohar.
Manohar, sir, good question. Sir, actually, generation of fuels from plastics is involving a process called depolymerization. So what happens is I'll have to depolymerize and reduce their molecular weight. So during the process of reduction of their molecular weight and depolymerization, normally it happens by the use of some catalytic system. It is a catalytic system. They use some catalyst and also some type of temperature, thermal subjection. They are subjected to some thermal temperatures. So what happens when I expose them to any temperature, sir, the fumes and the soot coming off, the effluents that are coming off, I'll give one simplest example, PVC. It's a commodity, straightforward polymer. If I try to use that for such kind of application, during the depolymerization, it gives off some gas called hydrochloric acid, which is one of the raw materials. So when hydrochloric acid comes off, it reacts with oxygen, ozone, and results in the depletion of the ozone layer. So what happens is incineration. That's why most of the polymer recycling companies have not gone into the route of incineration. While incineration, even if I have little bit of PVC subatomic particles, it will definitely result in evolution of hydrochloric gas. So this is very toxic to the atmosphere. In fact, while processing of such kind of plastic, they racially discriminate PVC fellow. The PVC is always kept aside, and there is a special designer extruder for PVC rather than others. So the effluent which is coming off is very, very harmful, sir. So maybe I think that's why now people are going on circular economy. Means how do we have used it. There are tons and tons of plastics available now. How can I take it back for some effective utilization where it is not getting exposed to the humans as well as animals? So that's what the efforts are going on. And I think I saw one more question. People are putting more effort. How to... Hello?
Thank you.
Yes, sir. We are able to hear you, sir.
Yeah. So they are trying to develop more on biodegradable plastics, sir. Biodegradable plastics are the future. Sir, have I answered the question?
Yes, thank you.
Yeah, okay.
Thank you very much, sir. Audience, you have many questions. What are the best methods? Okay, so I would like to read just one more question for you, Bala, sir.
Yeah.
Okay, there is a general question from Dr. Minja. He says, any best method that you can suggest to overcome the harmful effects of microplastic waste?
See, as I was saying, there are no general methods. These plastics are there. Now, the best way is to initiate something like reusing it by mixing with something. Like I'll give one example. Let me give an example. Like polyethylene, less than 5 millimeter, we found about 1 ton. We cannot incinerate it, and I don't want to use it because polyethylene is costing about 45 rupees per kilogram. It's an expensive system. So now I have that 1 kilogram. I'm not going to incinerate because incinerate is the best option so that it becomes invisible. But what I would try to do is I will take and mix it along with the virgin polyethylene, if there are any virgin polyethylene. And this virgin polyethylene will be grafted, will be surface treated, so that I can make blend of waste polyethylene with the grafted polyethylene. Waste polyethylene which goes for a carry bag application. Now after blending with grafted polypropylene or polyethylene, it goes for a very good engineering application like the legs for your stools or maybe the tabletops. So it has got a very good mechanical property. So we can enhance. So this is what we'll have to approach initially. Immediately, madam, I cannot eradicate. I don't like him, but I cannot eradicate. We cannot do that because you look around. No, you are everywhere. The plastic is everywhere. So we'll have to go once slowly we'll have to get in. But yes, now people are very much aware. This biodegradation, for example, polyethylene packaging is getting replaced by polylactic acid, where the polylactic acid is edible also. You can have it. And the packaging foams, at least now in India, I have not seen. In Europe, the packaging foams are cellulosic foams. They are like popcorn. You can eat it. It is edible. It's like popcorn. So, that kind of things are coming now. So people are really worried and they are approaching, but you cannot do it immediately. That's my point. Maybe our next generation, we'll have to work hard to reuse all these existing plastics.
Yes. Thank you, sir. So participants, let's conclude the question and answer session. See, microplastics are very dangerous, very dangerous, that we are seeing in the newspapers, that, how they entered even the Arctic region, and it is there in marine organisms. In today's presentation also, we saw kgs of plastic present in cow's stomach, right? So now microplastics are present in marine animals' stomach. And recently it is, very recently they say that it is even present in human blood, right? So that is that dangerous. But as our speaker said, we will not be able to eradicate in one day. It is through our habits of research and education. We can surely face this challenge and overcome the challenge. You, the precious educators, will really bring this awareness to your students about this microplastic pollution, and you will encourage them to slowly reduce the use of non-biodegradable plastics in their daily life, right? I am very sure that this webinar is very useful to you and to your students as well. And researchers also have seen the research point of view, how the research team could do something very appropriate during this time of COVID by having biodegradable mask. So we are all very much encouraged and motivated by today's webinar and the speaker. We thank you heartily, sir, on behalf of Bharat Institute of Engineering and Technology and Indian Ceramic Society and CRESIHRD. Sir, now Dr. Manohar would propose the vote of thanks. He is our Secretary of Indian Ceramic Society, Hyderabad chapter. Over to you, Manohar, sir.
Thank you. It is my pleasant duty to offer a vote of thanks. First of all, let me thank the eminent speaker, Dr. Balasubramanian, my younger colleague from DRDO. I have retired from DRDO a long time back, and it was very nice of him to speak of these things. Actually, we are not very much aware. We are concentrating only on air pollution, but he has brought out aspects of some this microplastic pollution and how to combat it. And I also congratulate and thank all the researchers working with him. Please find out new ways and new products to use and recycle these microplastics. Then I thank Dr. Sophia Rani. She has conducted this session very well. And let us hope that many more such a lecture series will continue in future. I thank Dr. Dibakar Das for introducing the speaker. And of course, I must thank the audience. I was very happy to note that 115 people have listened to this lecture. So this shows how popular the speaker is and how popular the topic is. So thank you, audience, and thank you all once again. Thanks.
Thank you very much, sir. Thank you.
Thank you, sir. Thank you, sirs.
Thank you, madam. Thank you. Bye. Bye.
Bye. Dear participants, there is a feedback link in the chat box. Kindly fill the same so that you can get your certificates. I know many of you would have faced few problems while getting some certificates in the last Saturday webinar. We are extremely sorry for that technical issues. You have all sent me some emails. Please do not worry about it. Our technical team will work on it one by one, and surely you will get all your certificates. And this time as well, we will post the recorded lecture in the YouTube, and then we will send you the recorded link as well. So you have come here to learn something new and learn something great, and you have allocated your time for this precious learning. So we from Bharat Institute and Indian Ceramic Society and CRESIHRD, we appreciate you so much. And then we really want you to go and talk about this microplastics. You can read about it in the newspapers and even from internet. There are many pictorial representations of this. So I would really like you to go and educate your students, whether they are primary or college or anywhere. I would like you to go and educate them, and you can instruct or encourage them to avoid and manage such kind of plastic waste, right? Thank you very much. And feedback form is there in the chat box. So this meeting will be ended now. Just for 5 minutes, the feedback link will be there in the chat box. Kindly fill it, and then you can leave the session. Thank you.